Hello and welcome to the ASC video series. I'm Dr. Sean Perry. This is Introduction to Statistics, STA 2023. We're looking at a problem from Chapter 7 concerning the standard deviation of the mean. So before we begin, it's probably best to go over a little bit of what we're talking about when we say the standard deviation of the sampling distribution, or when we talk about the sampling distribution in general. So let's pretend we're talking about some distribution of single values, which we'll call x. And just for fun, let's say that it's actually normal. So that is to say it's got a certain mean, it's got a certain standard deviation, and these are x's, perhaps, on the axis here. Now, what we want to consider is taking a sample of size n. When we consider samples of size n, we're going to be looking at a different distribution, but it's related to the previous one. We'll say that it has a center at mu of x bar. And again, what we're talking about here is sort of the average of averages. If I were to consider the average of samples of size n, and we were to consider taking many such samples, then these would have their own mean. But the average of those averages, or the mean of that average, would be the same as it was before. The center of the data will not change. However, the spread of the data, the standard deviation of the data, it will change. It will shrink. So we will get a taller, spikier bell curve than the one we had before. And this new smaller standard deviation, the sigma of x bar, is going to be our original sigma divided by the square root of m. So for n greater than 1, that's going to be something smaller, and we'll get a narrower distribution. You can find these relations right here in your formula sheet, as well as some formulas for z-scores. The main focus of this chapter is contrasting the difference in standard deviations between talking about individuals and talking about samples of size n. Just to be clear, what is the sampling distribution of the mean? So that's this distribution down here, which is in terms of x bars. These are distributions of averages of samples of size n, contrasted with the distribution of individual values, x. So here we have a problem from the homework. It says, the mean weight of all Goliath groupers caught on the Treasure Coast is 388 pounds. The standard deviation is 64 pounds. Suppose that we take a random sample of 59 Goliath grouper from the Treasure Coast, and we catch them and we weigh them. Let's determine the probability that the average weight of this sample is within 15 pounds of the average weight of all Goliath grouper caught on the Treasure Coast. Round the solution to 4 decimal places. Okay, so let's begin with a little sketch of the given information. They told us that the mean was 388 pounds, and that the standard deviation was 64 pounds. They didn't tell us what the shape of this distribution is. It need not necessarily be normal, but that's not going to matter. What's going to matter is that as we take samples, in this case of size 59, what will happen is this distribution of means will change its shape and will become normal. This is perhaps what is so fundamentally important about the normal distribution. Even if you start from a distribution which isn't normal, we don't know what it is, the distribution of means will become normal. So when we look at the average of x bar, that will be a normal distribution. So it's sort of like a fundamental shape related to sampling distributions that we get this curve. It's for all reasonably well-behaved distributions as you take larger and larger samples. And in general, we want this to be above 30. That's the rule of thumb. The technical reasons for why 30, I think, are beyond the scope of the course. Suffice it to say, if you're taking samples greater than size 30, you can treat the distribution of means as if it were normal. And this new mean has the same value as the old mean. Its standard deviation is given by the old divided by the square root of m. And calculating, that's 8.33209 and so on. It'll be something irrational unless your sample size is a perfect square. So let's consider the problem again. What they want is the probability that the average weight of the sample of 59 Goliath grouper is within 15 pounds of the average weight of all Goliath grouper. So the average weight of all Goliath grouper is this one. And the average weight, so this is an X bar that goes on this axis to contrast with an X here. The average weight, they want this to be give or take 15. Just a quick glance, this is 8.3 for our standard deviation. So with 15, we're talking about a little bit less than twice that. Just to make a nice sketch. We actually know those values, we could calculate them to get 373 and 403. And so the question about probability is essentially the question, what is this area? The probability of being within 15 from the average, from the global average, when I take some sample average, is going to be given by this area. There's a correspondence between these two things. And we could find that out using the calculator's normal CDF function. We could type in our lower bound, our upper bound, our mean. And for our standard deviation, I'm going to put in 64 divided by the square root of 59. The reason I'll type all of that in is to avoid rounding error. Else, I would have to take some value here and round my standard deviation. If we're going to use the calculator, let's use the full power of the calculator. We can put arguments here and not have to round and not take that error if we don't have to. Again, just to get a visual of what that's going to look like, we're going to do second vars to get to distributions. We're going down to normal CDF. We give a lower bound of 373, an upper bound of 403, and a mean of 388. And this is going to be our standard deviation of the sampling distribution. So we want 64 divided by the square root of the sample size, which is 59. If we didn't put that in there, this would just be the probability of an individual grouper being between these two values. There we go. So this is 0.92818 and so on, which we round to 0.9282. Let's look at a related problem. So suppose the standard deviation of the weights of all Florida manatees is 54 pounds. Let X bar be the mean weight for a sample of a certain number of Florida manatees. What sample size will give the standard deviation of X bar equal to 9 pounds? First, let's record our given information. We are given that the standard deviation of all Florida manatees is 54 pounds. And then they said that we want the sample size that will give us a standard deviation of X bar equal to 9 pounds. And so the question is, what is N? Now, there is a formula for this in the sheet. There is a formula for N in your formula sheet. However, it's also easy to get that formula. So sigma of X bar is equal to sigma divided by the square root of N by definition. So we can multiply the square root of N to the other side, divide by sigma of X bar, and then square to get rid of the square roots. However, there is a small problem here that will occur if this is not an integer. Because if this is not an integer, then neither will its square be. So I'd like to just include one addendum to that formula, which is this funny symbol here, which means round it up. Even if you get a decimal here, and we might not for this problem, but if you ever do, just round it up. So from here, we just evaluate, plugging in for sigma and sigma of X bar, 54 and 9. This is an integer, so its square is also an integer. And rounding this up, well, it has zeros on the end. So actually rounding it up just gives you 36 again. And there we are. All right, I hope this has been helpful to you, and good luck with your studies.